Hi, I'm Deepti. I'm a software engineer at Google, and I'm here to talk about WebAssembly. So, what is WebAssembly? WebAssembly is a portable, efficient binary format. So say you have a C, C++, or a Rust program, you can compile it to WebAssembly and run it on the web. So there's a couple of interesting things on the slide. The first one that says that the initial version of WebAssembly has reached cross-browser consensus. What this means is that representatives from different browser vendors like Chrome, Firefox, Edge, WebKit, they've all agreed on what the API surface should look like and the binary format. The other super exciting thing to me is that WebAssembly is being designed in an open standard in a community group, W3C community group. So aside from the fact that it includes representatives from all of the major browser vendors, there's also representatives from Intel, ARM, different companies that are potential users for WebAssembly. So some of the things that are awesome about WebAssembly are that it's efficient and fast. It's load time efficient in the sense that it's designed as a binary format, so it's fewer bits over the wire, and it's more efficient to load. It's fast because it tries, by design, WebAssembly tries to make use of hardware capabilities to give it the speed that it needs. So it's safe because it tries to enforce the same origin security policies that are in use in the rest of the web. The other exciting thing about this is that it's part of the open web platform in the sense that it can call in and out of JavaScript. It uses the same API surface that JavaScript uses to use browser functionality. And I think the important thing to talk about here is also what WebAssembly tries to not be. It is not a replacement for JavaScript. By design, WebAssembly should interoperate well with JavaScript. If you noticed our logo, it has this tiny slot on the top where the JavaScript logo is supposed to kind of fit. So it's definitely not a replacement for JavaScript. The other thing to note that it is not a programming language. I guess you could think of it as a programming language if you think of assembly as a programming language as well, in the sense that this is something that the compiler should generate and not something you should be writing by hand. You can write it by hand to try it out, but to make it efficient and get it to use all of the optimizations, you want the compiler to generate this for you. It is not a plugin in the sense that it's internal to the browser engine, so it shares the same stack. The other important thing that you want to note here is that it's not a target for dynamic languages yet, in the sense that we have proposals that are ongoing that we're exploring to support GC'd objects in WebAssembly, so you can have different languages that are not limited to a linear memory model like C, C++, or Rust. So one of the primary motivations for WebAssembly is that you want native code on the web. So what exactly is native code, and why do we want it? So if you look at applications now, there's more and more complex applications that you want to port to the web. These are game engines, image decoders, a whole variety of compute-intensive, performance-intensive applications that you want to port to the web. And ideally, you would want these to work at near-native speed, so have the performance that native applications give you. You want it to be portable in the sense that you want to compile once and run on different platforms. So you want it to be safe. You want it to run in a sandboxed execution environment. So those are the things that native code offers you, and these are some of the primary motivations for working on WebAssembly. The other interesting thing is that you have all of this existing native code that uses WebGL, different native capabilities that you can now compile to run on the web. One of the reasons why WebAssembly is actually useful is the fact that it's challenging to use machine capabilities through JavaScript. So if you have threads, SIMD, these are things that are easier to use if you're on a native application, but you have to jump through a whole bunch of hoops to actually be able to use any of this on JavaScript. There have been previous attempts to get native code on the web. One of these was Chrome's solution, which is Portable Native Client. This gave you performance, security, a lot of native functionality, but it was only supported on Chrome, so it wasn't portable. I mean, it's portable in the sense that you can run it on different architectures, but it's specific to Chrome, and you can't possibly run it on Firefox because of architectural limitations. The other, Mozilla's approach to this is actually ASM.JS. So let's talk a little bit more about ASM.JS. So ASM.JS is a subset of JavaScript that can be optimized and used as a low-level target for compilers. If you see that program on the right there, so one of the things about JavaScript is that it's a dynamically typed language. So the engine has to do a lot of work to figure out what types exist in your program and optimize according to those. ASM.JS gets rid of some of that in the sense that it uses type annotations for its parameters and return types, so you can optimize based on that. You can give the compiler, give the engine a hint and say, okay, use ASM, and it would try to use the specific subset of JavaScript that ASM.JS specifies. So why not just use ASM.JS? Why do we want a whole different thing like WebAssembly? First off, slower startup. That's also known as parsing is expensive. ASM.JS is a textual format, so textual formats are usually orders of magnitude slower than binary formats to parse. So that's it gives you it kind of hinders speed in that way. You also have limited functionality. What do I mean by this? It's just that ASM.JS is still a subset of JavaScript, so there's a whole bunch of things that you can't actually use, like 64-bit integers. If you have loads and stores, you need to, unaligned loads and stores, you need to mask them. It's, again, harder to get to CPU-specific features. The other thing is that even though you're kind of giving the engine a hint that says use ASM, on a validation failure, this falls back to regular JavaScript. So the performance in this sense can be inconsistent. The most important reason why we cannot use ASM.JS is that it's not a standard. So different browsers have different ways that they optimize ASM.JS. So you have varying levels of performance across browsers. So we're at the Node Summit. Why are we talking about WebAssembly? First off, Node 8 supports WebAssembly. So Node 8 is built on top of V8 5.8, which enables WebAssembly by default. So you kind of get this for free. The other thing is that one of WebAssembly's high-level goals is actually to support non-web embeddings reasonably well. And WebAssembly modules can be imported into a Node.js app, so you can expose WebAssembly functions for use via JavaScript. So what are the benefits of having a WebAssembly module in your app? On the back end, because WebAssembly is a portable IR, you can ship a single binary to any platform in the sense you build once and you can ship it for different platforms. The important thing to note here is that portability comes with a cost. So if you want portability, there's a chance that you're making a performance trade-off in the sense that your native binaries are always going to be faster. I mean, with caveats, but your native binaries will be faster because they can directly go to the machine code. But it's just something to keep in mind whether you want portability or whether you want the same speed. Another way to think about this is think about your app in general. So you have the client side and the server side. So on client-side applications, there are things you do like image compression and language detection and other things, mainly image compression. Let's take image compression as an example. This is something that if your image is large enough, you would want to send to the server. But with WebAssembly, you can do this kind of compression on the client side itself, so you can kind of rethink what goes on the client side and what goes on the server. So we talked about importing a WebAssembly module into your Node.js app. So what does a WebAssembly module look like? So this is a WebAssembly module. A WebAssembly module has linear memory, which is a contiguous byte addressable range of memory, and it can go from like the offset of 0 to whatever dynamic memory size, and you can also dynamically resize this memory. A table is similar to a linear memory, so instead of being bytes, these are opaque values of particular table element type. The main use of this in the WebAssembly MVP is we use this for indirect calls. Other interesting elements of the module are you have globals. So you store a single value of a fixed type in a global, and that's it's kind of separate from your linear memory, so it can't be arbitrarily accessed. Functions obviously are the most interesting part of your module because they have all the code. So these are the basic building blocks of a WebAssembly module. So the WebAssembly module can also define imports. So a module can declare a sequence of imports at instantiation. Optionally, these can be memory, table, functions, globals. The main point here to note is that you can only have one linear memory and one table right now in the MVP. You also have exports. So a module can declare a sequence of exports that are returned to the host environment at instantiation. So with all of this, I've been talking about instantiation. So the instance is the one that has all of the static state that you need to run a module. So if you look at this, like the imports and the exports are, kind of open-ended in the sense of how you interact with your host environment. So you can import functions that are defined by the host environment that can interact with your WebAssembly module, or you can export functions from your WebAssembly module to your host environment. And it's kind of open-ended what you want to do with it. So we've been talking about a WebAssembly module. What does it look like? So there's two things that have been defined in the MVP, which is the textual format and the binary format. So the code below is what the disassembly of a function looks like. So this function is just like an arbitrary function that has some memory operations, and it takes two parameters, and it adds them. So if you look at it, the first section is the textual representation of the function. So, and you have a one-to-one mapping at the bottom to the binary format. Everything on the left is offsets. So the actual compressed code is just so if you look at it, if you look at the I32 add line, 6A is the opcode for I32 add. So you can see how much it's been compressed. So it's just a string of bytes that represent that function. So if we want to take a step back and see what a module looks like. So this is a WebAssembly module. And it's just, again, it's a string of bytes. Everything on the left-hand side is actually just offsets. And you can see what the bytes after the colon. In the sense, the first colored section there represents the binary version. You have a section that defines what functions are present. So you have, you have a function. Number of functions is 1. The signature index. You also have a memory section, which defines the number of memories, memory index 0, what are its limits, etc. In this case, we have one exported function, so the export section also defines that. And the function body is what I've kind of splayed out there to look at. So how is WebAssembly implemented in V8? When we look at this, this is how your V8 parses JavaScript code. So I'm sorry, V8, the compiler pipeline. This is what the compiler pipeline of V8 looks like, kind of glossing over some of the things there. But if you have JavaScript source code, it gets parsed, and you generate these ASTs, and the JavaScript graphs are then get inlined, lowered, and passed to the JavaScript optimizer. So you have, it tries to figure out what the type information is and run all of these optimization passes. So how does WebAssembly fit into this picture? So what the WASM compiler does is WebAssembly is already optimized. It has static type information, so you just directly feed it into the machine graph, which goes to the backend, and it generates machine code specific to the platforms, which could be on Intel, ARM, MIPS, whatever a native code you want to generate. So there's some things that I want to point out here. We've been talking about performance. We've been talking about speed. Some of the caveats that you should take into account is performance is really tricky to measure. So based on your bench, if you decide you want to port something over to WebAssembly, this doesn't mean that this will make it fast on all your benchmarks. It's on a case-to-case basis. It's just there's a lot of things that you have to worry about when you're doing performance measurement. The other thing that is also important to note is WebAssembly is an emerging standard. So there's use cases where you assume that WebAssembly is fast, and in case it's not, we have bugs like everybody else does, and it's something that we're still working on. The other important thing to note is you have to use the right language for the job. So if you have computation-intensive programs or CPU-intensive programs, WebAssembly makes a good case for you. It makes a good case for you to use port your application to WebAssembly. But if you don't, there's cases where JavaScript does the job right, and there's cases where WebAssembly is the right way to do it. Ties into the same thing that WebAssembly tackles specific use cases, and it's not a blanket solution to all your performance problems. So what are some of the use cases that you can use WebAssembly for? You have encryption, video augmentation, game distribution, you have image, video editing. There's just a whole bunch of applications, server-side computation of untrusted code. There's a lot more applications and use cases that I haven't actually put on the slide, but you kind of get the general idea there. So we're at MVP, and what are some of the post-MVP features that we're actually considering? So we are considering threads, atomic operators. It's basically to provide low-level building blocks for pthread-style shared memory. You shared memory between threads. You have atomics and futexes. The other thing that we're exploring is fixed with SIMD. We've made efforts to do this in JavaScript with SIMD.js, but it's been tricky in the sense that it's probably not going to be as performant in the JavaScript cases. There's not as many use cases, but it fits well into the WebAssembly use case. There's also exception handling. You can emulate exception handling through JavaScript, but it gives you the correct semantics, but it's not going to be fast. So one of the things that's in progress is zero-cost exceptions. So I talked a little bit earlier about C, C++, and Rust, and use these modules in compile these to WebAssembly. So we want to be able to support different languages. So what do we want to do when it comes to dynamic languages? We're trying to build, build like a garbage collection mechanism that can efficiently allocate and manipulate GC objects in WASM code. So, contributing. Like I said earlier, with WebAssembly, one of the high-level goals is that we want to work well for non-web use cases. So, we appreciate input from different web communities to see if this actually fits their use case. If it doesn't, we would love for you to come up to us and tell us why it doesn't work. There's a lot of information on WebAssembly.org, including a really cool tanks demo that's based on the Unity engine. There's also lots of tips and tricks to get started. The GitHub page is up there. Like I said earlier, we work as a part of the W3C community group. We have regular meetings that are over VC and sometimes in person to discuss use cases, to discuss future features, to discuss implementation, like all the kind of applications that we're trying to cover. So, if this is something that interests you, we would love for you to come up to us and tell us how this doesn't cover your use case and talk about it to the other implementers as well. Thanks.